Welcome back to CIS 209. This topic is going to be on keys. We've got lots of different types of keys, as we will see shortly. Our objective for this topic of keys is to identify the different types of keys and give you some tools to allow you to do that. How do we determine what a candidate key might be? How do we determine how to select a primary key? We'll be able to demonstrate how primary and foreign keys link related tables. The primary key of the one side to the foreign key of the many-side relation. Then determine insert, update, and delete restrictions based on those keys. So here are different types of keys. A little bit of terminology here. Candidate keys is a candidate key is one or more fields that could be used to construct a primary key and thereby guaranteeing uniqueness. Now you'll find that in many data sets, in many relations, you might have 2, 3, or even 4 different candidate keys as combinations that would guarantee uniqueness. A primary key would be the key that uniquely identifies a row on the table. Again, could be one column, could be more than one column. One of the key things is that no part of a primary key may be null, which means having no data in it. So every column must have some data in it if you're going to go for more than one column. But a primary key is the key that uniquely identifies a row on a table. So an alternate key would be a candidate key that did not get selected for a primary key. So typically we'll see that to produce a natural key, a primary key that's a natural key, we would select the best candidate key. And therefore, once we've selected one of those candidate keys, all the rest of the candidates that were not selected become then alternate keys. And a foreign key literally is a copy of the primary key value from a particular row in a one-side relation that when placed as a foreign key column in a many-side relation, the value would link us back to that row in the one-side relation. So here's some issues about candidate keys. Again, they must contain unique data. So if you have 3 fields, the guarantee is that the combination of those 3 fields would always guarantee uniqueness. Perhaps you've got a phone number plus an address plus a birth date, and you're going to choose that as a candidate key for your person. Again, all 3 of those fields must have data in them, no nulls in any of those, and they would always guarantee uniqueness. Now there could be security issues if you took a field like a social security number. You might not want to use that because you may need to display it, and that's personally identifying information. So you might want to disallow something as a candidate key if you have issues about displaying it for security purposes. So your list of candidates then will become the basis for selecting a primary key if you're not using what's called a surrogate key. We will be discussing surrogate keys in the very near future. So surrogate keys are primary keys that are generated by the system, therefore they're artificial. They're system provided, arbitrary. Many people create them sequentially, but there's no actual need to do that. You could create them randomly as long as they were guaranteed to be unique. So they are a type of primary key. They differ from a natural key in that they do not contain data that's found on the row. So you have some theorists who we consider purists, C.J. Date being one of the most notable, who argues against the use of these surrogate keys because he feels they're a violation of relational principles and that all the data on a row should be data about an instance of the entity. They're not data, though. They're just a marker that is unique, and therefore they guarantee uniqueness. But do, however, have all the elements of a good primary key. So again, some theorists argue that because they're not derived from data, they really shouldn't be used. So let's discuss some characteristics of what makes up a good primary key. Of course, the first characteristic is that it must provide uniqueness on the row. The second characteristic is no part of that primary key, if it's more than one column, can be allowed to be null. Another more practical aspect is that the values just don't change. You don't want to be updating a primary key. You want it to be stable over time. One of the other interesting things is you want it to be minimal, and again, not multi-part. You find some primary keys are code sets. So for instance, you might, on a purchase order, have a location number plus a date be part of the purchase order number. You really don't want to do that. You want no coded sets. You just want them to be minimal. If it's a natural key and not a surrogate key, it'll then determine all of the fields on that row via functional dependency. We'll try to explain a little bit more about functional dependency a little later. Standard practice then is also to use the name of the table as a prefix with maybe an underscore and then an ID suffix. So customer underscore ID perhaps. But characteristics of the good primary key also is that it's numeric. Numeric primary keys make better indexes and typically are faster to process than character-based columns. So for primary and alternate keys, remember each relation must have a primary key. It can have alternate keys, which again are unused candidate keys. One consideration that, again, CJ Date brings up is that if you're going to use surrogate keys, then you must place a unique index across the alternate keys. A unique index is simply something that acts very much like a primary key. It prevents you from duplicating that alternate key, which is a good thing. So it prevents inadvertent duplication of those alternate keys. So one thing you want to think about, if you're going to use surrogate keys, you still need to identify your candidates, because those are all going to be alternate keys, and you'll want to place unique indexes across those to block inadvertent duplication of the row. A unique index is called a constraint. Again, it acts like a primary key. So it's a good idea, even if you're using a natural primary key, to take all these alternate keys you find and place unique indexes across them to, again, prevent inadvertent duplication. So non-key columns would be all the other columns that are not involved in any kind of a key. So relationships, we want to talk about how keys work in relationships. So on the one-side relation, you're going to have a column that's going to be the primary key, one or more columns. This key, one or more columns again, is also the basis for the foreign key on the many side. Must be the same data type and length. So if I have a numeric primary key column, I want to have a numeric foreign key in the many-side relation that links me. So for any given row in the one-side relation, its primary key value will be found in the foreign key column of each many-side related rows. So let's say I have a customer with 20 orders. The customer ID would probably be in the primary key of the one-side relation customer. Then I could also have a customer ID field in the order table, and there would be my foreign key in the order table that's going to link me back to customer. So for any given row, for that customer who has those 20 orders, in each row of those 20 orders, in the foreign key column customer ID, I'd have the value of the primary key of that customer in the orders that were placed by that customer, and therefore provides me linkage back to the one-side relation from the many-side order. Another interesting aspect of relationships is that you'll find that the many-side relations are where the majority of the data and therefore the action is. In fact, your intersection or associative relations in transactions hold the most data. So a given customer may have placed 20 orders. Let's assume that each of those orders has 5 ordered items on it. That would give me 100 rows of data in the order item table relative to the 20 orders that were placed by the one customer. So you'll generally see your queries hitting those intersection tables to do things like totaling and to see how many items have been ordered over a given time period. Most of the query action is going to be in that intersection table of ordered item. They will hold the foreign key link values that allow us to retrieve data from the one side. So the order item would have an order ID as a foreign key, which will lead us back to the order table. The order table will have a customer ID foreign key that links us back to the customer. So here we have what's known as the transaction pattern. This is at the very highest level a many-to-many relationship between customer and product. See, customer and product being related many-to-many, but that's at the very high level. As we find out more about how customers interact with products, we stumble upon this thing called the order. So a customer places one-to-many orders. We find the foreign key, customer ID, a replication of the primary key in the customer table. Once we've established the relationship that one customer can place many orders, and many orders can be placed by one customer, each individual order placed by one and only one customer, then we ask the relationship between order and product. And we discover that a product can be on many orders, and an order can contain many products. So we resolve that with an intersection entity called ordered product. You'll see the primary key of ordered product has the order ID from the order, the product ID from the product. And there's other fields like the ordered quantity, shipped quantity, and product price. So this is typically called a transaction. The point here is that much of the querying is going to be done around the ordered product. But the ordered product only contains IDs. So to turn the data into information, we're going to follow the product ID as we join up back to the product name or price. We would have the order. We'd need to know what the customer's name was as opposed to the customer's ID. So the relationship links would be that you need the order ID of the parent order when querying the ordered product. I also need the customer name, but the name is on the customer table. So I'd have to, again, link ordered product to order on the order ID and link the order to customer on the customer ID, and allowing me to present data that users can easily use instead of trying to make them understand what an ID means.